Awesome, thank you. First of all, I'd like to thank the organizers of this meeting. This is a great opportunity for me to meet a lot of my collaborators, get a lab, and enjoy this fantastic city. As mentioned, my name is Daniel Tennant. I'm a postdoc in the group of Adrian Lupascu at the University of Waterloo. But actually, I live and work in Boston at MIT Lincoln Lab as part of the measurement component of the QEO program. So the work I'm presenting is the culmination of a lot of people's hard work. And so if I forget any names or anything, it's just because I'm talking in front of a lot of people, and I apologize in advance. One of the main goals of the QEO program is to build and perform experiments on a highly connected, highly coherent quantum annealing processor. As I've gained an extra appreciation this week, actually, the more connectivity for a finite number of qubits means the more number of interesting problems that we can embed in these types of architectures. So this high connectivity kind of demands the need for long-range coupling as we extend qubit-qubit interactions across our device. So one way of do that without sacrificing coherence, or an idea for it anyway, was proposed by Jamie Kerman a few years ago with this coupler tree network. So this is a really interesting idea, basically building kind of a network of squid-like devices that acts as a medium through which qubit-qubit interactions can propagate. So this is kind of, this has some nice features due to the fact that we don't have to extend the loops in our either qubits or couplers and introduce a lot of destructive flux noise, and also really change the functionality of our devices as we change their geometry. So earlier this week, we heard about some really exciting results from the Lincoln Lab team from Cyrus, and concerning 1- and 3-dimensional coupler chains, or not 3-dimensional, but 3-unit coupler chains. And we think our work that I'm going to present today complements that pretty well. So we've been able to design, fabricate, and begin experiments on a number of different devices. The design of these devices was done mainly by basically 2 incoming graduate students, which is a bit impressive. Denny Melanison and Antonio Martinez at the University of Waterloo. And I should also say this was kind of hand in hand with Sergey from Northrop Grumman and Jonathan Yoder from the fabrication team at Lincoln Labs. It was a really nice collaboration and an experience, a learning experience. So each of these devices has some kind of specific experimental objective, kind of towards building a larger coupler tree network. The single qubit is sort of like a canary in a coal mine. Along with these devices, the program's also debuting a new qubit environment. And so this single qubit device is our first man in test of this new environment. We also have a dimer device, which is just 2 qubits coupled by a single coupler to show just a simple example of coupling between qubits. And we also have it wired up for some interesting noise experiments and the effect of noise on annealing probability. So we're kind of excited about that science experiment. The YQY device is really to test the effect of this network of active couplers on the coherence of a qubit that's embedded kind of in the middle of it, and make sure it's not too destructive. The coupler chain, as you can probably surmise, is to evaluate like how well we can actually propagate these signals through a long chain. And the AQC2019 device is our first step in really building high connectivity with these signals branching out in multiple directions. Should note each one of these coupler and qubit units has its own tunable resonator associated with it. So these devices are starting to get fairly large for our program as it stands right now. They are, the qubits in these devices are these 4-junction capacitively shunted flux qubits, which we've heard about in a few talks before this week. They're basically an extension of the highly coherent 3-junction qubits developed by Fei Yan at MIT, where we basically replaced the, there it is, small junction with a DC squid. So we have extra tunability and function in these devices. So if we can thread flux through the Z loop and control the chirality of the persistent current, and also adjust the magnitude of that persistent current through the X loop. We also have tunable couplers that I'll talk about in the next slide, and then these tunable resonators for readout, which also have some nice capabilities. So how do these couplers work? We want some kind of small signal, small flux signal, maybe from an adjacent qubit, to enter in the Z loop and have some large effect or a large susceptibility. Once we have that, that's going to be proportional to the coupling energy that goes into our interaction Hamiltonian. So how do we tune this device such that we have that large susceptibility? And if you remember from the Hamiltonian that describes these Josephson circuits, there's a term that goes like phi squared and is proportional to the geometric inductance of the circuit. There's also a Josephson inductance, which is proportional to the cosine of that phase. So if we have too much of one, for example, too much of the geometrical inductance, our wave function is going to be stuck in the bottom of that well, kind of regardless of how much flux we put into our main loop. Likewise, if we have too much Josephson inductance, our wave function is going to be kind of stranded in one of those wells and again, not really be able to escape. But if we can kind of counter those two terms, we can create a potential energy that is wide and shallow such that any small flux that we put through this loop can kind of push the wave function to one side or the other and change the state of the persistent current. Shown here is some typical values of this interaction energy for a qubit coupler qubit as we tune the coupler Z flux. So it's kind of nice. We also have a positive and negative values of this interaction, so we can go back and forth between ferromagnetic and antiferromagnetic coupling. Our tunable resonators are basically little antennas with a Josephson loop at the end of it. So we can tune the frequency of that resonator as shown here. And these actually act and give us kind of a dual capability, which is kind of nice. So if we operate this resonator at its flux insensitive spot, it can act in a dispersive mode with the qubit. So as we tune the qubit Z and X bias, as we change the qubit frequency, that interacts with the frequency of our resonator, and as we probe at a particular frequency, the resonator passes through there, and we can see the periodicity of our qubit in that signal. We can also operate this resonator in a flux sensitive spot, and it behaves as a flux detector. So if we tune our qubit to its high persistent current value with this X flux, and then change the Z flux as we go from a left circulating state to a right circulating state, that induces a change in flux into our sensitive resonator at this point, and we see a jump in the frequency of our resonator proportional to that change in flux. So out of this one device, we get kind of like these two modes of detection, which is going to free up a lot of space on our future devices. As I mentioned before, these devices are also a debut of a new Qubits architecture and environment. The eventual plan for our program is to arrive at these fully integrated 3D structures proposed by Donna Rosenberg. But as a midway, kind of like towards that final goal for our 5-year program, these devices were fabricated in this 2-tier device structure where we have a qubit layer comprising of qubits, couplers, resonators, an interposer layer with our bias lines and all the wire bonding going to it. And then they're fabricated separately, and there's a few different kind of paths we can take in our fabrication and what we stick to what. And then they're finally bonded together through these conductive idiom bumps. So this is the first time we've shown this, or we've made devices like this, and so far the signs are pretty good. For example, we've taken T1 measurements, and we've shown that there's not really a substantial decrease in coherence as far as these measurements go. These are on par with our single-tier planar geometries. And kind of for an added bonus, when we really started doing annealing experiments, it involves a large change in current around our qubits, and that induced kind of like a ring down in the electromagnetic environment around our qubits and resonators that you can clearly see in one of our old designs here. So this is basically doing an annealing experiment and then waiting some time to read out. And as you see, our resonator acting in this flux-sensitive regime kind of goes through this very long decay. And this was a big hindrance for our annealing experiments, because we'd have to separately tune up for every different annealing time or pause after anneal, we'd have to retune up the readout, which was a big pain and was eating up too much time. And this was also seen by the Santa Barbara and Google group in this paper here. And what they did to kind of like cure this was actually put their device in some superconducting package. And that kind of eliminated their long-term flux modes. It seems like we kind of have done a similar thing in this, basically like these two superconducting planes that kind of protect our qubits and resonators and provide a clean electromagnetic environment. So here we have just some like very short sinusoidal decay, and our resonator is within its DC value within a microsecond. To say a little bit just about the hardware, these experiments were done at Lincoln Labs in a light and dilution refrigerator. I got this slide from Cyrus. Thank you very much. This is probably the only photograph you'll ever see of the inside of Lincoln Labs. And my fridge is kind of hiding back there in the background. You can see it there. And some kind of like nice things about these refrigerators. We have some in-house traveling wave parametric amplifiers, which provide us with quantum limited amplification. And also we have a nice working relationship with Keysight. And to really perform annealing experiments on larger devices like the ones I'm going to show later in this talk, we really need a number of different arbitrary waveform generator lines that are all in sync with one another. And so these chassis with a number of different card slots and a number of different channels per card slot allow for that functionality. Excuse me. Okay, so some results from the single qubit device. Again, this is the same scan that I showed a few slides ago when describing the resonators. This is operating the resonator in its dispersive mode and then scanning through the cubic X and Z flux biases. One thing we noticed when we took really fine scans of this is that there's some features that kind of veer off to the side. And this was noted in Sergey's talk on Tuesday, that we strongly believe that these are due to asymmetries in the X-loop junction size. So even though the full crosstalk calibration is good, there's these local asymmetries that Jeff Grover spent a lot of time plotting out. And he was using just these kind of qubit scans here, but it was nice to see those results reproduced in spectroscopy scans. And again, they're well fit to this analytical function describing that asymmetry. What's a bit not disturbing, but something like we'll have to keep in mind as we move forward, even a modest amount of that asymmetry actually leads to a rather large effect. So we've also done annealing experiments on the single qubit device. Our experimental protocol is to start in the qubit's kind of high frequency, strong transverse field regime, offset to some small finite z-flux, and then anneal up along this constant z-flux along this, and so basically increase the x-flux bias to the high persistent current state of our qubit. As we do that, we perform single-shot measurements on the resonator, which is tuned up to be right there if it's in the right circulating state, and jumps somewhere else if it's in the left circulating state. And so we see a nice separation between the left and right circulating states in these histogram single-shot measurements. And we can get some width of this S-curve. And of course, our center is actually quite a bit pushed to the side due to this asymmetry. This is actually the initial clue I had that something was going on here. So a lot of work is being done right now, especially from Mustafa Kariz and Jeff Grover, in an attempt to really build models that explain these S-curves, not only in terms of Landau-Zener transitions, thermalization out of the ground state, but also kind of like the idiosyncrasies of our particular devices. So it's kind of like an ongoing experimental and theoretical path that's happening in QEO right now. Okay, so we've moved on about 2 weeks ago to start taking data on the coupler chain device. It is one of the largest devices we've had in our program so far. It's 2 qubits, 7 couplers, 9 tunable resonators with a total of 27 bias lines. So actually, like, almost takes up about half of one of those chassis already. This is just some kind of initial scans with the PNA as I biased couplers, 4's resonator. And you can see there's a number of different resonators that show up corresponding to different couplers and qubits. There's a number of different anti-crossings. It's kind of a daunting task to kind of start to calibrate these devices. But Shai Dai, one of the graduate students at Waterloo, has picked up on this computer vision technique and a way to identify and separate these different resonant lines within the same scan. So we can kind of identify this, for example, as a particular resonator, find the mutual from the bias line that we were actually tuning into this device, and then kind of like get the information from it. And this is especially neat because in this one scan, we can actually get a number of different mutuals. So this has the potential of really speeding up our calibration time. So just some preliminary results from this coupler chain device, kind of ignoring the inter-unit crosstalk. We can map out the qubits behavior and the couplers behavior for these different units. And we have some initial demonstration of flux transfer along this chain. This is operating qubit 2 at its high persistent current symmetry point and then scanning across in the Z bias. So the qubit is switching from a strong left persistent current to a strong right persistent current. And that flux difference is being seen in resonator 7, but then also, kind of unexpected actually, also resonator 3 and resonator for coupler number 1. What's kind of clued us into this is like the real thing, is that we are able to tune this jump from kind of left to right, or down to up, from up to down, signaling we've changed from, for example, a ferromagnetic coupling to an anti-ferromagnetic coupling, kind of exactly where we expected to. So this is just preliminary, but very promising results, and we're currently still taking measurements on this device. There's a lot of interesting future experimental work that we want to do. We have some simple, I say that very sarcastically, demonstrations of coupling through the chain, kind of similar to the measurements that, for example, Cyrus reported on Monday, basically avoided level crossings in the qubit spectroscopy. Also, what we'd like to do is park one of the qubits, for example, in a right circulating state, and then anneal the other qubit as a function of the coupler. So we should see the effective symmetry point of that other qubit shift around as a function of the coupler's strength, very similar to the results shown by Sergey on Tuesday on another device. There's also been a lot of work developing multiplex readout in our program by Simon Gustafsson, Roni W., a postdoc in Will Oliver's lab, and Steve Dissler from NGC. And so now we can, with this ability, we can actually start to measure correlation functions across the chain. One of the postdocs at Waterloo has been investigating the correspondence between this coupler chain and one-dimensional magnetic systems, Salil Beckenthal. And there's actually been some interesting recent theoretical results from this institution that show that these response functions that we now have the possibility of measuring have some real connection to basically a measurement of quantum entanglement. So in conclusion, along with the results from MIT Lincoln Labs, we have some initial demonstrations that these highly connected, long-range qubit-qubit interactions are possible. This multi-tier device architecture for coherent, tunable qubits has a viable path forward. We've developed some, we think, really useful automated device calibration tools to use on this and future devices. And we're really looking forward to these kind of like interesting science experiments using this multiplex readout. So I'd really like to thank everybody that I kind of work with on a day-to-day basis. All these guys from Northrop would have been on the author list, but for legal reasons. And so, yeah, it's a real pleasure to work with this talented team of scientists. So thank you.
Questions here?
Hey, Daniel, very cool data. The annealing curve that you showed, the S-curve for the qubit transition, was that done with just a straight-up anneal, or was there some correction for asymmetry that you also baked in?
This one here?
Yeah.
No, this is just a straight anneal along the flux lines.
Okay,
yeah.
Thanks.
Can you give me an idea when you expect to have some coherence information for the long coupler chain experiment?
We are in the process of really doing, I wanted to get some preliminary data, and we're in the process of doing a real calibration, which we'll probably spend another week or two on. And then spectroscopy and coherence time measurements are certainly on the docket.
Thanks.
Yep.
There is a question here.
One of the things I would find really helpful if everyone got on the same page in terms of quoting coherence times in reference to something. And that something is the anti-ferromagnetic energy, interaction energy. So just think of the two local energy there. So in particular, the numbers you had, like tens of microseconds. I'm just guessing that's probably where tunneling energy is like 5 gigahertz, right?
I see you like here.
So, yeah.
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 Yeah. So what really matters, so you can think, I mean, the trivial reference point you can think of it, for instance, is where is the quantum critical point for a 1D chain? So it's where the coupling energy and this tunneling energy are crossing. So you really need to look at that point where they're comparable. And I know at that point coherence times are certainly starting to dive, because what's happening is you're actually coupling to the flux degrees of freedom in the environment much stronger. In this regime here, you have a monostable potential. You're primarily seeing the effects of dielectric noise, in fact.
Yeah, thank you.
Yeah, so the way I've always phrased this is in terms of a quality factor. You can just take that frequency for the coupling energy, coherence time, gives you a Q. So my guess is you're sitting somewhere around 10. We are likewise sitting around 10. Interestingly, the ion traps used to be sitting around 10 too, despite their seconds long coherence times.
Okay. Yeah, thank you.
Is there another question here? No?
Yeah. Do you have evidence or maybe just an intuition of why these chains of coupler should be better than doing minor embedding? Like,
Sorry?
do you think these chain couplers would be better than doing minor embeddings and building chains like we are used with?
Yeah, we're not really trying to solve a problem.
What?
We're not really trying to solve a problem with the chain, but rather show a functionality. So I'm not quite sure how to answer that. Yeah, but.